Hi, this is Math 2520, and this video is over section 8.8, and we're going to look at numerical integration. You've seen something similar to this in Calculus 1. It's called Riemann sums. It's where you're using shapes to basically approximate the area of a curve. And so that it should be a little bit of a reminder of some stuff you've seen. Sometimes not all functions are nice derivatives, and example would be like e to the negative x squared. It's not going to have a nice elementary function that's the derivative. Other things would be like square root of 1 minus x to the fourth, or natural log of x, things like that. And so we have to use sometimes approximations to find these integrations. And this is where this is going to come into play. So with Riemann sums, we looked at left Riemann sum, right Riemann sum, the midpoint Riemann sum, and we found that, you know, the left or the right could be either over approximation or under approximation, and normally the midpoint was the more accurate approximation. But in all of these, we are using rectangles to kind of estimate the area, and the more rectangles we use, the better the estimate would be, because that made the rectangle smaller, and it's like you're adding up more precise pieces. All right, so in this, what we're going to look at is a couple of these different approximations. One is going to be the midpoint rule. Then we'll look at trapezoid rule, and then we'll look at Simpson's rule. Okay, and they're going to each be a little bit different in how they approximate it, but a lot of it's going to be kind of like procedure oriented with how we go about it. So first, with the midpoint rule, we're going to divide an interval from a to b into n subintervals of equal width, and so that width is going to be b minus a over n. This is something straight from the Riemann sum. And then we're going to let x sub 0 equal a, which is going to be less than x sub 1, which is going to be less than all the way through x sub 2, x sub 3, up to x sub n, which is going to be equal to b. And then x sub I for each of these, so your x sub 1, x sub 2 is found by a plus that delta x. And so once we have our x sub i's, we can find our corresponding y values, and we're going to let y sub I equal f of x sub I, and this is going to give us a height of our rectangle. And then we're going to sum up these areas. All right, so if we look at this as the integral from a to b of f of x dx, and it's going to be approximately the change in x and the summation from I going to 1 to n of f of x sub I. Well, x sub I bar is equal to 1/2 x sub I minus 1 plus x sub I. So it's basically average of the previous x sub I and the next x sub I. And so we have these rectangles here. This is going to be x sub 1, x sub 2, x sub 3, x sub 4, and then a and b are your x sub 0 and x sub n. And each of these is going to have a rectangle associated with it. First rectangle is going to go from a to x sub 2 horizontally. And we can see that there's going to be a little bit overshoot here and overshoot on this side as well. And the next one, and then the next one, and then the last one. Okay, so 5 different rectangles. Alright, so let's use the midpoint rule to approximate the integral of x squared from 1 to 5 using 2 rectangles. So first our delta x we have to find. This will be 5 minus 1 over 2, which is going to equal 2. And so x sub 1 bar is going to be 1/2. And then you'll have x sub 0 plus x sub 1. And then x sub 2 bar is going to be 1/2 x sub 1 plus x sub 2. Okay. Alright, so for your x sub 0, it's equal to 1, starting point. Your x sub 2 is equal to 5. And that's your ending point. And then your x sub 1 is 2 added to the first one, so that'll be equal to 3. So we'll have 1/2 1 plus 3, which is going to be 2, and 1/2 3 plus 5, which is going to be 4. Alright, so x squared. I'm going to graph this from 1 to 5. And at 1, it's equal to 1. At 2, it's equal to 4. At 3, it's equal to 9. At 4, it's equal to 16. I'm trying to make this so it makes sense and spaced nicely. Alright, so it's part of a parabola. So it looks something like this. And we're doing 2 rectangles. So first rectangle is on this side. It's an overshoot. Second rectangle is on this side. It's an undershoot. So, idea is they average out kind of thing. Alright, so the integral from 1 to 5 of our x squared dx is going to be approximately equal to, remember, we're not doing the integral here because we're approximating it, to our delta x and a summation from I equaling 1 to 2 of f of x sub I bar. So approximately it's going to be 2 times the summation of our f of x's. So we'll looking at x sub 1 bar squared plus x sub 2 bar squared. So 2, x sub 1 bar squared is 2, so it'll be 2 squared plus 4 squared. And so we'll have 4 plus 16, which is going to be 20, times 2, which give you 40. Okay, so that's our approximation. So let's look at what it would be exact, because this is the integral we can do. We take the antiderivative, you get x to the third over 3, integrate this from 1 to 5. So this would be 5 cubed over 3 minus 1 cubed over 3, which is going to be 125 over 3 minus 1/3. That's going to be 124 over 3. And when you divide that, you get 41.3 repeating. Okay. Pretty close to our approximation of 40. And this didn't even use really small rectangles or anything. Right. So let's do another one. We're going to approximate 0 to 2, x squared plus 1 dx, that integral. We want to do it with 4 subintervals. Alright, so first our delta x is 2 minus 0 over 4, which is going to be 0.5. Then we're looking at our subintervals. So x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Zero starts out at, the first one starts out at 0, last one ends at 2. And we have to go and space this out by 0.5, so 0.5, 1, and 1.5. Alright. And so now we look at x sub 1 bar, x sub 2 bar, x sub 3 bar, and x sub 4 bar. This is going to be, remember, these x sub bars are 1/2 the average, or basically it's the average of each of the first two. So we're going to do 1/2 of 0 plus 0.5, 1/2 of 0.5 and 1, 1/2 of 1 and 1.5, and 1/2 of 1.5 and 2. So this will be 0.25, this will be 0.75, this will be 1.25, and this will be 1.5. Right, 3. Yeah. No, that's not 3. That's I'm adding 2. That's 3.5. I was multiplying. So this will be 1.75. Knew it had to be 1.75. I just didn't know what I was doing wrong in my head. All right. So those are our x sub bars. So now we find f of 0.25, f of 0.75, f of 1.25, and f of 1.75. Right. So it's just, put this into your function. 0.25 squared plus 1, 0.75 squared plus 1, 1.25 squared plus 1, 1.75 squared plus 1. Right. So each of these, this comes out to be 1.0625, 1.5625, 2.5625, and 3.0625. And so now your approximation for your integral will be your delta x, which is 0.5, times the summation of these four. So 1.0625 plus 1.5625 plus 2.5625 plus 3.0625. And this comes out to be about 4.125. Now, if we were to find the exact, I'm not going to do this for everyone, but if we were to find the exact one on this, we are looking at x cubed plus 1, x cubed over 3, plus x integrated from 0 to 2. So this is going to be 2 cubed, which would be 8/3, plus 2, and then 0s on both. And this is about 2.67 plus 2, so about 4.67. So a little, the approximation is a little lower here, but it's still in a good range. Right. So now we'll integrate from 1 to 3, 2x plus 3, and we're going to approximate it. We'll again do 4 subintervals. So our delta x is going to be 3 minus 1 over 4, which is going to be 2/4, which is 0.5. Our x sub 0 is going to be 1. We have 4 of these, so it'll be x sub 1, x sub 2, x sub 3, and x sub 4. The last one's going to be 3. And so x sub 1 is 1.5, x sub 2 is 2, x sub 3 is 2.5. And so now we find the middle points of these. So x sub 1 bar is the average of 1 and 1.5, so it'll be 1.25. X sub 2 bar is between 1.5 and 2, so it'll be 1.75. X sub 3 bar is 2.25, and x sub 4 bar is 2.75. And then we want to find our f of x sub 1 bar, f of x sub 2 bar, f of x sub 3 bar, and f of x sub 4 bar. And so 2 times 1.25 plus 3 that would be 2.5, 5.5. And then 2 times 1.75 plus 3. Let's see. That would be 3.5. That'd be 6.5. Okay, 2 times 2.25 would be 4.5 plus 3 would be 7.5. And then 2 times 2.75, which is going to be 5.5 plus 3 would be 8.5. Okay. So now we want to find the sum, or the approximate sum. So this is 1/3 integral from 2x plus 3 from 1 to 3 is approximately equal to 0.5 times the sum of those four, 5.5 plus 6.5 plus 7.5 plus 8.5. So this is going to be, let's see, 1112 plus 16 over 2. So 28 over 2 is 14. Again, if we were to integrate this, we would have x squared plus 3x integrated from 1 to 3. It's going to be 9 plus 6 minus 1 plus 3, which would be 15 minus 4, which is going to be 11. So it's a little bit off, but not far. All right. Next rule. They follow very similar procedures. It's just more of a few differences here and there that you have to memorize. With the trapezoid rule, instead of making a rectangle, we make a trapezoid like this. This is f of x. This is f of x plus 1. This is x1. This is x. And so the area here would be f of x sub I plus f of x sub I plus 1 over 2 delta x. So basically averaging these two functions and then multiplying it by your change in x. And the way it will work with a curve, x sub 1, x sub 2, x sub 3, is you're creating these trapezoids. Some bigger than others. Some going down left, some going down right. But it's meant to approximate that curve, and I believe this one is better of approximation than the midpoint. Right, delta x is found the exact same way. B minus a over n, where n's your subintervals. Your x sub i's are found the same way. The difference comes when we're summing it up. Instead of delta x times the summation of all the f of x sub i's, there's a 1/2 on the first one and a 1/2 on the last one. Or you pull the 1/2 out, so you divide your delta x by 2, and then you have 2's on all the middle ones, which I think is the easier one to follow, because you just gotta remember to multiply everything in between by 2. Right, so And we're approximating x e to the x from 0 to 8 using 4 trapezoids. So n equals 4. First thing is let's find our delta x. It's going to be 8 minus 0 over 4, be 2. And so your x sub i's, so x sub 0, x sub 1, x sub 2, all those. I'm waiting for this to finally finish saving. Alright, so x sub 0 will equal 0, x sub 1 will equal 2, x sub 2 will equal 4, x sub 3 will equal 6, and your last one, x sub 4 equals 8. Right. Now, one of the differences with this is we do not average our x sub i's. So once we have our x sub 0 to x sub 4, we use those. Right? And so that is one thing we won't have to do. One big difference between the midpoint rule and this rule. Then we find our x sub i's. And so we'll do 0 e to the 0, 2e to the 2, 4e to the 4, 6e to the 6, and 8e to 8. And we won't actually find values here. Just leave it how it is. Right, so now let's approximate this. Integral from 0 to 8 of x e to the x is approximately a delta x, which is 2 over 2. And then we'll do our f of x sub 0, which is going to be 0 e to the 0, plus 2 times our 2e to the 2, plus 2 times our 4e to the 4, plus 2 times our 6e to the 6, plus 8e to the 8. Right, so we'll get 1 on the outside, and so this equals 1, this equals 0. So we'll have 4e to the 2 plus 8e to the 4 plus 12e to the 6 plus 8e to the 8. Okay. And then if we put this in a calculator, we get 29,155.15. Right. The exact value for this, and you can maybe do this on Desmos, is 2867.71. So, you know, it's a bit off in terms of about 9,000 off, but in thousands, it's still kind of close. All right, so we'll integrate from 0 to 1 e to the x. I'm going to do this with 4 subintervals. So first, our delta x is 1 minus 0 over 4, which is 0.25. And so our x sub 0 is 0, x sub 1 is 0.25, x sub 2 is 0.5, x sub 3 is 0.75, and x sub 4 is 1. And so we'll have f of x sub 0 is e to the 0. F of x sub 1 is e to the 0.25. F of x sub 2 is e to the 0.5. F of x sub 3 is e to the 0.75. And f of x sub 4 is e to the first. Okay. So now the integral approximation is 0.25, that's your delta x, over 2 times e to the 0 plus 2e to the 0.25 plus 2e to the 0.5 plus 2e to the 0.75 plus e to the first. And so when we put this in a calculator, you'll get approximately 1.7272. Right. I'll do one more of the trapezoid rule. I'll do integral of from 0 to pi of sine x for subintervals. And we'll do this from 0 to pi. So our delta x is pi over 4. So x sub 0 is 0. X sub 1 is pi over 4. X sub 2 is pi over 2. X sub 3 is 3 pi over 2. And x sub 4 is pi. I'm sorry, 3 pi over 4 is x sub 3. Right, and then we find f of x sub 0, which is sine of 0, which is going to be 0. F of x sub 1 is sine of pi over 4, which is square root of 2 over 2. F of x sub 2 is sine of pi over 2, which is 1. F of x sub 3 is sine of 3 pi over 4, which is square root of 2 over 2. And f of x sub 4 is sine of pi, which is 0. Alright, so now the integral from 0 to pi sine of x dx is approximately equal to delta x, which is pi over 4, over 2, f of 0, which is 0, plus 2 times f of 1, which is square root of 2 over 2, plus 2 times 1, plus 2 times square root of 2 over 2, plus 0. So this is going to be pi over 8 times square root of 2 plus 2 plus square root of 2. Okay, and we will get approximately 1.9069. The actual integral of this is equal to 2. you can do the integral and find that out, but yeah, it's equal to 2. Okay, so now with Simpson's rule, he uses parabolas instead of trapezoids or rectangles. And so for this, the area of the parabola here is going to be delta x over 3, and then, assuming 3 spaces here, we'll do y sub 0, then 4 times y sub 1, and then y sub 2. So y sub 0, 4 times the next one, and then you go back down. Last one's always just by itself. So delta x over 3, y sub 0 plus 4, y sub 1 plus y sub 2. So it's similar in adding a 4, though we don't always add a 4. If you notice, we'll add 2 and it'll alternate until we get to the final one. The final one's always by itself as well as the initial one. And then we're always dividing the whole thing by 3. The rest of the stuff does stay very similar. Delta x is still b minus a over n. One major thing here, though, is n must be even, otherwise you can't use this. And you still find your x sub I is the same way. And the reason n has to be even is otherwise you won't end up with the right number of terms. So if we want to find 0 to 8 of x e to the x, which is an integral we have already done, but we're going to use the Simpson rule instead, and we're going to let n equal 4. So first, delta x is 8 minus 0 over 4, which is going to be 2. Okay, and n is even, so that checks out. So x sub I, x sub 0 is going to be 0, x sub 1 is going to be 2, x sub 2 is going to be 4, x sub 3 is going to be 6, and x sub 4 is going to be 8. And then your f of x sub I, first one is going to be 0e to the 0, which is 0, 2e to the 2, 4e to the 4, 6e to the 6, and 8e to the 8. And so for Simpson's rule, the approximation here is going to be delta x, which is 2, over 3, f sub 0, which is, it's just going to be 0, plus 4, 2e to the 2, plus 2, 4e to the 4, plus 4, 6e to the 6, and then the last one, plus 8e to the 8. Right. And so if you put this in a calculator, you get approximation of 22,683.9, which before we got 2867 as our exact, and our trapezoid was 29,155. So this is much closer to that exact of 20,000. Alright, so this is Simpson's rule. Alright, so we'll do the next one. delta x is going to be 1 minus 0 over 4, so 0.25. So x sub 1 or x sub 0 is 0, x sub 1 is 0.25, x sub 2 is 0.5, x sub 3 is 0.75, and x sub 4 is 1. And these are x sub i's. F of x sub i's, we get 0 cubed is 0, 0.25 cubed, which, now I'm going to switch these to fractions so it'll be easier to cube them. Let me get the fractions here. So this is 1/4, 1/2, 3/4, and 1. Alright. So 1/4 cubed be 1 over 64. 1/2 cubed would be 1 over 8. 3/4 cubed would be 27 over 64. And 1 cubed would be 1. And so our Simpson's rule, integral from 0 to 1 of x cubed dx is approximately delta x 0.25 over 3 times 0 plus 4 times 1 over 64 plus 2 times 1 over 8 plus 4 times 27 over 64 plus 1. Okay, let me get this simplified some. So this is 1/4, so this would be 1/12. And then divide both of these by 4, you'll get 1/16 plus, I'm going to put this all in terms of 16 to make this easier. So 2/8 would be 4/16 plus, and this is going to be 27 over 16 plus 16 over 16. So 1/12 would be 5, 32, 48 over 16, which is 3 over 12, which is 0.25. Okay, one more we'll do sine of x. So our delta x is pi minus 0 over 4, pi over 4. X sub i's 0, pi over 4, pi over 2, 3 pi over 4, pi. So f of x sub i's, sine of 0, sine of pi over 4, sine of pi over 2, sine of 3 pi over 4, and sine of pi. So last one, the first one are 0, middle one's 1, and the other two are square root 2 over 2. Right, so using Simpson's rule, the integral is approximately equal to pi over 4 over 3, 0 plus 4 square root 2 over 2 plus 2 times 1 plus 4 times square root 2 over 2 plus 0. Right, so we're going to simplify this. Pi over 12, 2 square root 2 plus 2 plus 2 square root 2. And this comes out to be approximately 2.6153. Okay, the last thing here we'll do is a actually no, we got two more things. We're going to do a application problem. This deals with mechanical engineering and stress and strain curve generated by experimental data. The area under the curve represents the energy absorbed by the material or the toughness of the material during deformation, which is before it fails. So material undergoes a tensile test, and the following stress values are measured at different strains. So for 0.0 strain, you get a stress of 0. 0.1, 50, 0.2 is 100, 0.3 was 120, 0.4 was 130, and 0.5 was 125. We'll find the area on the curve, which represents the energy absorbed, until it reaches a strain of 0.5 using Simpson's rule. All right, so delta x. Okay, we're going to use these as our x's. X sub 0, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. So our delta x is 0.1. Okay. So now we're going to find, using Simpson's rule, delta x 0.1 over 3, and then f is 0 plus 4f of 0.1 plus 2f of 0.2 plus 4f of 0.3 plus 2f of 0.4 plus f of 0.5. All right, and we know most of these values. They're in our table. So we get 0.1 over 3, f of 0 is 0, plus 4, f of 0.1 is 50, plus 2 times 100, plus 4 times 120, plus 2 times 130, plus 125. So we get 0.1 over 3, 200 plus 200 plus 480 plus 260 plus 125. And this becomes 0.1 over 3 times 1265, which ends up being 42.17. And then this is the energy per volume absorbed by the material. Okay. Last thing, this is approximating errors in our numerical methods. There's an error for each type, using the midpoint, using the trapezoid, using the Simpsons, because these are not going to come out to be exact. They're all approximation. And so we look at the error boundaries. Second derivative has to be less than or equal to some k value, where x is still between a and b. And then the absolute value of our midpoint error is k b minus a cubed over 24n squared. For the trapezoid, it's very similar, but it's a 12 on the bottom instead of a 24. And then for Simpson's rule, we use the fourth derivative and that absolute value. And that has to be k b minus a to the fifth less than k b minus a to the fifth over 180 n to the fourth. So let's say we wanted to find the max error used in using s to the 6. So Simpson's rule, n equals 6, to calculate the integral of 1/3 cosine of 2x dx. Right, so first, let's find our delta x. We're doing 6 subunits, so it's going to be 3 minus 1 over 6, which is about 1/3. Right. And so our derivatives, first derivative would be sine of 2x over 2. Second derivative would be negative cosine of 2x over 4. Third derivative is negative sine of 2x over 8. And then the last fourth derivative is cosine of 2x over 16. Right, and this has to be less than 1 over 16. And so our error, oops, meant to do absolute value, e to the s has to be less than 1 over 16. 3 minus 1 to the fifth over 186 to the fourth. Okay. Which is 1 over 16 to the fifth over 186 to the fourth. And this becomes 1 over 116640, which is about 8.57 times 10 to the negative 16. Right. I may have skipped over a little bit. The k value here, we did this because we had to find something that this fourth derivative is going to be less than. And so we get 16 on the bottom. That's why we have the 16 here. And then cosine's max value is 1. Cosine of any angle, its max value is 1. So that's why we set the k as 1 over 16. So that's where that came from. And then you move into this to find the max error. Let's try this for the trapezoid rule. Delta x be 8 minus 0 over 4, which is going to be 2. First derivative, we use product rule, x e to the x plus e to the x. And the second derivative, we have to do the product rule again, x e to the x e plus e to the x plus e to the x. And so we get 2 e to the x plus x e to the x. And with the idea that, this is going from 0 to 8, we can compare this to 8 e to the 8 plus 2 e to the 8, which is less than or equal to 10e to the 8. And this is where we're going to set our k value. Okay, so the absolute value of e to the t, or e of t, error, I don't know what to call that actually, just the error itself, is your k value, 10e to the 8, 8 minus 0 cubed, over 12, 4 squared. Remember, we're using trapezoid, so we're using that. That's why that's squared and the top one's cubed. And so this is 79,492.2. Pretty large error, max error. All right. So how large should we take n, or how large should we take n to be in order to guarantee that the trapezoid approximation is within 0.1? All right, so again, k is our 10e to the 8. We have 10e to the 8, 8 cubed over 12 n squared. And we want that less than 0.1. So 10e to the 8, 8 cubed over 12, 0.1 has to be less than n squared. And so n, and reverse this, n has to be greater than square root 10e to the 8, 8 cubed over 12 times 0.1, which comes out to be 3566.34. So n has to be greater than or equal to 3567. Okay, so in all approximations that we've been doing where n equals 4, the error has always been really large of what we could have for a max error. If we were to get a large n, like 3,567, our error shrinks down to something really small, and so like we wouldn't have something like 9,000 like we did in which problem was it? Like in this one. Okay, we had 9,000 error, about 9,000, pretty large error. For our n equals 4, we have something like 4,000 for our n. We're going to get much smaller error. I mean, we don't always get large errors. We only have an error here of 0.1 for the most part. But there is a way to not just find the approximation, but also find what the error is, depending on what your n is. All right, in the last section, chapter 8, we'll look at improper integrals. I'll see you then. Bye.